Today's session is going to go over the end of lesson 6. It's the reading assignments on electronics, semiconductors, and on TV and radio. So let's start with electronics. So when electrons fly off of a piece of metal, it is called electron emissions. And there are 4 ways to get electron emission to happen, all of which require a voltage to be applied to the conductor as well. One is to apply heat to the conductor. Another way is to apply strong light. Another way is to apply a very high voltage. And the last way is to strike the conductor with electrons from another source that knock more electrons loose. A diode is a sealed tube which has a conducting terminal on each end so that it can connect to a circuit. The inside of the tube is either a vacuum, where there are no molecules at all, or filled with a non-reactive gas. When a current is flowing through the circuit, electrons move one way through the diode. They are emitted from the end called the cathode, and they flow towards the end called the anode. The current through a diode can only flow one way. If the battery is flipped around so that the negative side is attached to the anode instead of to the cathode, no electrons will flow through this diode. Your text describes this with diagrams of a switch. So in those diagrams, it works when the switch is in a position allowing the negative side of the battery to be connected to the cathode. So just like this, but there'd be a switch in place making that happen. But the diode doesn't work when the switch is in a position connecting the negative side to the anode. Okay, so if it's this direction from the negative to the anode, it doesn't work. So we need to remember for this next part to make sense, alternating current changes direction many times each second. So since a diode only lets current flow in one direction, using a diode on an alternating current gives an interesting result. The alternating current normally switches from positive to negative, but the diode doesn't let that happen. So the negative parts get cut out and we're left with the positive half of the wave, with gaps in between. When a diode is used to do this, it's called a half-wave rectifier. Now, having those gaps in the electric current is weird, so you can also put in a second diode that goes in the opposite direction, keeping only the current that flowed in that other direction, which fills in the gaps in the current. A setup with 2 diodes like this is called a full-wave rectifier. In addition to diodes, there are also triodes, which have an extra feature. A grid in the middle has a negative charge, and the strength of that negative field can be adjusted. By making it very negative, it prevents electrons from flowing to the anode. But by making it almost neutral, just a tiny bit negative, it lets lots of electrons flow to the anode. In a cathode ray tube, the cathode emits electrons, and a grid and an anode and some deflecting plates are used to control the beam of electrons. So they're emitted here and originally just come out of the cathode, and then right away they start to be controlled. We've got the grid and the anodes, and then you've got these deflecting pairs that change direction, and it controls where that beam of electrons goes. the end result is that the electrons hit a screen and cause it to glow. So cathode ray tubes were used in TVs and monitors before the use of LCD screens, and they still have industrial and medical uses. Bombarding some materials with electrons, such as the material tungsten, bombarding them with materials with electrons at certain velocities makes the metal release X-rays instead of releasing more electrons. This happens in a vacuum tube with a cathode to release the electrons and the tungsten acting as an anode. So at this point, I want to go over this chart that appears in your study materials, where it lists the different types of electronic devices that we talked about and their properties and their uses. So I'm going to show you the way that I fill out this chart, and it's actually a little bit different than the way your text does. So if you look at your answer key, it doesn't necessarily mean that one way is right or wrong. They're just going to be a little bit different. So this is just a quick review and to help you fill that chart out. And then it might be a good idea to keep this chart handy while you're taking your test because it covers a lot of material. So the first one is electron tubes, and that actually includes everything below. So these different diodes can be electron tubes. There's other ways to have diodes, but in general, their properties is that you've got electrodes, which is a cathode and an anode, sealed in a tube, and the electrons move from the cathode to the anode. So they're used anytime you want the current to flow one way. You can use an electron tube. A high vacuum diode, its properties is that it's an electron tube where the electrodes are sealed in a tube with no air, and the electrons move from the cathode to the anode. They also only allow the current to flow one way. A gaseous diode, similar except that it's got a non-reactive gas inside. It also allows the current to flow one way, and the gas can actually become ionized and neutralize built-up charges around the cathode. And we just talked about using diodes as rectifiers. It's basically just any of these diodes, but put into an AC current circuit, which is an alternating current circuit. And the uses for that would be you start with an alternating current circuit, but if you use two of these diodes as rectifiers, you get a full wave rectifier, giving you a continuous direct current. And then a high vacuum triode is sort of like a high vacuum diode, except it has the three parts: anode, a cathode, and a grid. And the purpose of that is to control the voltage going through the circuit and be used as an amplifier. And this chart continues. If you're watching this video later, you can definitely pause this and copy down what you need to, or go back and watch it again if you need to. But I'm going to move on to the end of the chart, which is these last two cathode ray tubes. So their properties, they create an electron beam, and that's controlled with a grid, an anode, and deflectors, and they end up hitting a screen that glows. And their uses are medical uses, such as oscilloscopes monitor voltages, and one of uses for that is medical, to monitor your heart's activity. And old TVs and monitors, they also use cathode ray tubes. And the last one was X-ray tubes. There we go, which is a cathode that shoots electrons at the anode, and the anode releases X-rays. So what are they used for? Usually imaging, where the X-ray hits, hold on, can't see what I wrote. The X-rays hit a screen, and if there's an object in the way, then it blocks the X-rays from the screen and makes a shadow on it. And some things that we can't see through don't block X-rays. So they're helpful for seeing inside of things that we can't see through with our eyes. And here's a review question for you before we move on to the next section. So in a triode, what makes the electrons get to the anode instead of sticking to the grid? So here's our options. I'm going to give you a few seconds to think about it before I bring it up. But in a triode, what makes sure that the electrons get to the anode instead of sticking to the grid? Is it because the grid is neutral, the grid is negatively charged, the grid is positively charged, or the grid is an escape route for electrons? And the answer for that one is that the grid is negatively charged. So if it was positively charged, then the electrons would move towards the grid, and the electrons, which are negative, they would encounter that positive charge and they get pulled toward it. So positive is no good. Okay, neutral isn't very helpful either. That wouldn't do much of anything, but because it's negatively charged, it pushes the electrons away from it and they continue on their way moving towards the anode. And this option was just an extra one that doesn't really make much sense. So the grid is negatively charged, and that helps the electrons get past the grid and get to the anode. All right, this brings us to our next section, which is the reading assignment on semiconductor devices. So we have learned in previous sections that electrical conductors are materials that allow current to flow through them easily, and electrical insulators prevent the flow of current. There is a third type of material called a semiconductor, which is somewhere in between. Semiconductors, such as silicon and germanium, permit some flow of current. So they're not as good as conductors, but they don't inhibit the flow the way that insulators do. They're somewhere in between. That's why they're semiconductors. And you should probably know that these are the two materials used as semiconductors, silicon and germanium. So when a semiconductor exposed to heat or bright light, some of the electrons in it are knocked loose from their atoms and they travel to another area. Oops. Let me go back. Sorry. All right, they're exposed to heat or bright light. Some of the electrons are knocked loose and they travel to another area of the semiconductor, but they leave behind a positively charged area called a hole. Okay, so your electrons are negative, but the holes that they leave behind are positive. Because the location of the holes can change, the holes are considered to be positive charge carriers, and the electrons are negative charge carriers. So in other circumstances, we learned very early in this chapter, or this lesson, the electrons move, the negative charges move, and the positive charges usually don't. So semiconductors are about the only place where we ever talk about the positive charges moving, because the holes can change position as different electrons move around. And semiconductors can conduct more effectively if the material has certain impurities added. Different impurities have different effects on the conductivity. There are two types of impurities resulting in two types of semiconductor. You have impurities that make N-type material, which releases electrons, and P-type material, which collects electrons. So this is super important because N-type material emits electrons and P-type material accepts electrons. If the two are put together, the current easily flows from the N-type to the P-type. It cannot reverse because the electrons won't move from the p-type to the n-type. When the two materials are put together, the place where they touch each other is called a junction. Because the current only flows one way through the junctions, we say the junction between semiconductors is biased in one direction. If the positive battery terminal is attached to the N-type material, like in this image on the screen, it is pulling the charges away from the junction. This is said to be reverse biased. If the negative battery terminal is attached to the N-type material, then it is pulling the charges toward the junction. This is said to be forward biased. Okay, because the junctions between an N-type and P-type material only let the current flow one way, this is called a junction diode. Junction diodes are used to control current and act as rectifiers for AC circuits, just like the electron tube diodes that we discussed in the last section. But junction diodes are better than electron tube diodes. They are smaller, they are more rugged, more durable, and sometimes they are more efficient. So these are two different ways to do the same job of making sure the current can only go one way. And because of that, we could use either of them to act as a rectifier in an alternating current, making sure only the positive current goes through. So two pieces of semiconductor material are put together to make a diode. Three of them put together make a transistor. A PNP transistor has a wafer of N-type material in between two wafers of P-type material. An NPN transistor has a wafer of P-type in between two N-types. The middle wafer of either type is called the base, and the outer wafers are the emitter and the collector. The junctions between them have names, so the junction between the emitter and the base would be called the emitter junction on either one, and between the collector and the base would be called the collector junction. And the transistor will work differently based on which type of transistor it is and how the voltage sources are connecting to it. These details are called bias conditions. Your text focuses on the bias conditions of the PNP transistors. So that's the ones that we'll be looking at on the next slide. So the setup of a transistor with an emitter, a collector, and a base is kind of similar to a triode with a cathode, anode, and grid. The transistor performs the same functions as a triode, but with several advantages. The transistor is smaller, more rugged, has a longer operating life, and it doesn't require a hot cathode to use, which means there's less power used and less warm-up time. So once again, these two items, you've got transistors and triodes, they perform similar functions, and they're just two different ways to do it. In general, transistors are better for these reasons. Now let's look at how the bias conditions of a PNP transistor affect the flow of current. First of all, electrons don't easily cross any junction unless there is a current and an outside voltage source applied. Now, looking at a PNP transistor, where you have the P on the outside and the N in the middle, if the positive terminal of the battery is connected to the base like this, and the negative is connected to the collector base junction is reversed bias. The current will not flow easily through this transistor like this. But when another voltage source is applied with the positive terminal connected to the emitter, it makes the emitter base junction forward biased. So this side was reverse, but this side is forward biased. And this is actually going to allow a current to flow across the entire transistor. So to reiterate this one more time, for a PNP transistor to be forward biased, it needs two voltage sources. On one, the emitter is connected to the positive terminal, like this. You have the emitter and the positive, and this wire goes between them. And the base is connected to a negative terminal. This makes the emitter base junction forward biased. Then on the other side, the collector has to be connected to the negative terminal, okay, which it is through this wire, to the negative. And then the base has to be connected to the positive terminal. When a transistor is set up with these voltage conditions, the output voltage is very large. So the power is amplified greatly. So it's an important thing to remember about this type of transistor. If it's set up correctly, the output voltage is very large without changing the current much, so it acts as an amplifier. The power is amplified greatly. And your text shows a way to simplify this whole transistor into diagrams that are a little bit simpler. These diagrams will show the transistor as having two circuits. An input circuit on the emitter side, that would be here. That's your input circuit. And an output circuit on the collector side, which goes there. Whoops. These diagrams show it having two circuits, like I said, the input and the output, and both of them share the base in the middle. So the base is part of both of those circuits. Okay, so before we can move on to the next section, we've got a couple more review questions. So junctions between the N-type and P-type materials are biased in a direction. So which is which? Pulling charges away from the junction is blank, and pushing charges towards the junction is blank biased. So I'll give you a couple seconds to think about it before we get the answer. So pulling charges away from the junction is reverse biased, and pushing charges toward the junction is forward biased. All right, and one more review question. In an NPN transistor, is the base P-type or N-type? Is the collector P-type or N-type? Or is the emitter P-type or N-type? So NPN means on the outside we have an N-type, in the middle we have a P-type, and then on the outside we have another N-type. So the first one that's easiest to answer is the base. The base is in the middle, so the P-type is the base. And that means the two on the outside are the N-type. So both the collector and the emitter are N-type material in a NPN transistor. And if we used another type, if we used the PNP transistor, it would be reversed. And the last reading assignment for this lesson is about radio and television and how those signals get created and transmitted. So, when the frequency of an alternating current going through a conductor is high enough, some of the energy is emitted from the conductor as radio waves. Radio frequency waves are at a higher frequency than humans can hear. They are waves that are greater than 30,000 hertz. Radio frequency waves can carry information stored in the pattern of the wave itself. So there's two different ways that this is done. Either the pattern in the amplitude, either the pattern is stored in the amplitude of the waves, which is called AM waves, which will look like this. So your sound pattern is shown in the amplitude of the waves. So in this waves, it's the height away from the starting point. Or the pattern is shown in the frequency. So if this is our pattern, it's shown here in the frequency of the waves, how they get further apart and closer together at different intervals. So this is why we have AM radio and FM radio. The AM, all of the waves carry a pattern like that, and FM, they all carry a pattern like that. So to actually transmit the radio signal, there's some different parts of the radio. The oscillator converts DC current to AC current at RF frequencies. A transmitting antenna is the conductor that actually emits those waves. A microphone picks up on sound waves and converts them into an electric current with the same pattern as the sound waves. And a modulator is the part that gives the pattern to the waves produced by the antenna. The waves sent out by the antenna are called carrier waves because they carry the signal in the modulation pattern, as we just saw on the previous slide. Okay, so those are different parts of the wave for transmitting or sending the radio signal. And then to receive a radio signal, the tuner sets the device to only respond to a certain frequency. So if you have an older device that's analog, old car radios and old just regular radios in your house, they've got these tuners displays where you move the needle up and down to be at the right frequency, and then you'll be able to hear the radio at that frequency. In newer radios, it's digital, where you just press a button that says go to the next one, go to the next one, and you just go forward or back, and it'll automatically find that frequencies for you that are available. So that's the tuner that sets the device to only respond to a certain frequency. An RF amplifier strengthens the current. A demodulator separates the pattern from the carrying wave. So remember, a modulator is what created that pattern in the waves, and the demodulator takes it and separates the pattern out from the carrier wave. And then you have a loudspeaker that converts the currents of electricity into sound waves for people to hear. So that's how the sound is transmitted for radio. For TV, though, first the visual image must be converted into a pattern that can be easily transmitted. To do this, a screen gives off a pattern of electrons based on the patterns of light that are on the screen. The electrons create this same pattern on a metal target. Then a scanning electron beam measures that pattern, and a modulator codes it into a wave just like the radio transmitter. Note that this is an explanation of how analog signals were sent until recently. Modern digital TV transmissions use a similar process, but they don't code the signal into the FM waves anymore. Uh, Either way, once it's coded correctly into the wave, then the signal is transmitted and it's received in a similar way to the radio. Okay, and that's the end of that section. Oh, there's the waves being transmitted, sorry. Okay, so we got some other review questions about this. So first of all, are these devices for transmitting or for receiving radio signals? So remember, transmitting means sending the signals out, and receiving means receiving the signals. So all four of these are one of them. Oscillator, antenna, microphone, modulator. Are they for transmitting or receiving? I'll give you a few seconds to think about it. And those are for transmitting. And our second question, number 2, match those devices up to their functions. So I'll give you a little bit longer to think about these because it's kind of a lot to read and I can read them out loud. So which one of these does each of these functions? A, which one sends out radio waves having the same frequency as the current supplied by the oscillator? Which one, B, enables the waves produced by the antenna to carry the pattern of the sound waves picked up by the microphone? C, which one converts a direct current into high-frequency alternating current? And D, which one picks up sound waves and converts them into a suitable electronic current with the same pattern as the sound waves? Okay, so here's our answers. A is an antenna, B is a modulator, C is the oscillator, and D is microphone. And that takes us to the end of this section, which is the end of lesson 6. So if you're watching this recording later, you can definitely ask questions about this or anything else in this lesson. You can email your questions to your instructor, or you could call in and ask to speak with an instructor.